We're looking at section 2.1 today, but before we do that, let's take a minute to look at the syllabus again. So on Friday we looked at the quiz dates. And we set one up for February 29th. Did anybody see there was a problem with that? Somebody emailed me after, a couple people did actually. There is no February 29th. Okay, so you do have a quiz. Quiz 1 is March 1st. So the Friday after February 22nd is March 1st. You can go ahead and cross that out. The other two quiz dates are going to just be the way they are. While we have the syllabus open, I wanted to remind you on Wednesday you'll need a pine cone or a pineapple. Okay, so I see some of you already are on the ball, ready to go. That's great. Try not to eat the pineapple until then, all right? Okay, so we need it Wednesday. Wednesday, bring a pine cone or a pineapple. Does anybody need a syllabus? So in 2.1, we begin moving to think quantitatively. What does it mean to think quantitatively? What does that even mean? We have the word qualitative and we have the word quantitative. What does the word quantitative mean? Yes?
Thinking of things of values relating to numbers.
Right. Thinking of things in values related to numbers. So there's different areas where you'd want to think quantitatively, and that's what we're learning about in our math class. Can anybody think of one area of life where you'd want to think quantitatively? Money? Good. Good example. Okay, you think of the quality of your life when you're old, but you think of the quantitative way to get to that quality of life. So a lot of times qualitative and quantitative work together. What are some other areas of life where you would want to think quantitatively? Yes?
Baking.
Baking. Yeah. You have qualitative, how is that food going to taste? And quantitative, how are you going to get the measurements right to get there? Good. Anybody have any other ideas? Maybe if you have a small business, then you'll be wanting to think qualitatively there. Maybe some of you are going into government work and you'll have to be thinking of public policies, and those public policies will affect people's quality of life, but you'll have to take the quantitative measurements into account when you make those qualitative decisions. So lots of places to think quantitatively, and that's one reason I asked you to bring 1,000,000 items so you could start thinking about quantity. So please tell me 1,000,000 items that you brought. Somebody, what is yours?
I brought 1,000,000 grains of salt.
1,000,000 grains of salt. How did you know there were 1,000,000 grains of salt?
Well, I was originally thinking salt because there's a lot of, I looked up how much in like half cups. A half cup is 1,000,000 grains, but less than that is like 1,000.
Okay,
So I
good.
just made sure to measure it out right.
So you measured out a half cup because Google that
Yeah,
tells you
Google
1,000,000
measured.
grains of salt in one half cup. Good. Okay. And I see that looks like 1,000,000 of something. What is that?
It is 1,000,000 grains of rice.
1,000,000 grains of rice. And how did you know it was 1,000,000?
It took me a while. I didn't have a scale. I was planning on just, taking a cup or whatever and weighing it out. I don't have that. So I took a tablespoon, dumped it onto a plate, counted how many individual pieces of rice were in a tablespoon, and then figured out that and then did the math.
Wonderful.
So that's 1,000,000.
That's a great way to do it. So you measured out a tablespoon and counted it, and then you just could make multiples of that
Yes.
tablespoon. That might be something you want to post on the internet to save someone else that work. Anybody else bring 1,000,000 of something? I see another. What is your bag?
You're saying.
Sand? Okay. And how did you know you had 1,000,000 grains of sand?
I also used Google, and we kind of found that like a whole cup was 8 quadrillion grains of sand.
Wow.
So it was like 1/16 of a cup-ish is what they said is about 1,000,000.
A 16th of a cup to get 1,000,000 grains of sand. That's very interesting. It must be pretty fine sand. Yes.
I don't know if this is counts, but when I was thinking about it, I was like, oh, maybe I think it's something that represents something. So I brought a fork because you could like eat like 1,000,000 dishes in the world. Like it might represent like cooking or something in a place in the world.
So your fork is representing 1,000,000 dishes of food that you would like to eat someday?
Possibly, yeah.
Well, since 1,000,000 dishes aren't here, you're going to have to go dig up some salt or sand, but that is very creative thinking. Any other 1,000,000 items here? Yes.
According to Google, I found that there are 1,000,000 micrograms of acetaminophen and 2 Tylenol.
Oh, okay. So in the Tylenol, there's 1,000,000 micrograms of acetaminophen. Okay, that might be something other people have in their cupboards too. Any other 1,000,000 items? Yes, what is yours?
Bottle of water.
A bottle of water. What's 1,000,000 in your bottle of water?
1,000,000 water particles.
1,000,000 water particles. How many ounces did you have to have for that?
A drop.
1 drop?
Yeah, power of Google.
Oh my. Wow, interesting. Okay, almost everybody has that then. Did I see some other hands? What is yours?
I did the same thing she did, but with sugar.
Oh, okay, so you did sugar.
Yeah, like
Sugar.
a cup thing.
Well, 1 cup of sugar has the same. Well, you people did very well. Is there anything else that you have? I think that's what you take a picture of for your Dropbox today. Am I remembering right? Did anybody look? Okay, so take a picture of your water, if nothing else. And upload that sometime before Monday. So we're thinking quantitatively. Your author starts these sections out with a question. The question for today is how many ping pong balls are needed to fill up this classroom? So we're going to write that down. So how many ping pong balls are needed to fill up the classroom? So can you go ahead and make a guess? Write down your guess on your notes. You don't have to tell me what it is. I brought some ping pong balls. That maybe will help. Here's how big a ping pong ball is. Students at home, you can go ahead and look at your room and guess. Well, is that something we can figure out? How many ping pong balls are filled? Yes, we can figure that out. How would we figure that out? Yes.
I think I did it the hard way, but I would put them like on the tile.
Okay, put them on the tile.
And just kind of like fill it up that way.
That's a nice way to do it. So you have these square tiles on the floor, and if you had enough, you could just put them all out and then count how many, and then, yeah, that would be a nice way if you had enough. What is...
Based off of that estimation, divide the room into like a four-cornered shape.
Okay.
And there where there's kind of this weird shape, make like maybe a triangle or something, and then try to like do it by height, depth, and width. How many ping pong balls it takes to get the cubic
Sure.
measurement of how many ping pong balls would fit in this room.
So that's another way to measure the room and then find that cubic size and divide it by the number of cubic inches in a ping pong ball. I think that's the way we're going to use because I didn't bring enough to do the other way. Okay, so I'd like you to get in groups to do this. Maybe I'll put you in groups. How's that sound? So I'll put you in groups. Students watching online, please do this at home. That's why you needed a ruler. Hopefully somebody in your group will have a ruler. So as you measure the room, as you pointed out, this room has these like cutouts. Just ignore. Okay, ignore the cutouts and make this into a rectangular shape. And we'll get a very good approximation, even if it's not going to account for every little place. For example, the cutouts where the doors, where those triangles are filled in by the cutouts that make up the windows, you know. So we lose a little here, we gain a little there. So we'll get a good approximation. So I'll put you in groups. So how about this could be a group of 4 right here, and then how about U4, so U2, and then U3. U3 could be a group, okay? So 3 in your group, 3 in the middle. And then the whole back row will be a group. This whole back row will be a group. And then over here, how many people are there left?
Does anyone have a ruler?
Okay, so 10, we'll divide it here. So 10 people, 5 here for a group, 5 here for a group. So go ahead and measure the room. You can use the tiles that you notice. Come and get a ping pong ball too in your group.
Can I take one of these?
Yes, that's what they're set up. Yeah. Oh. There you go.
Thank you.
Sure.
Yeah, maybe just either a diamond, just the rectangle. So we measure this long, this long, and then we count a chair. So then we divide it by, we multiply it by 3 cubic measurements, and then this part here, that's 3 yeah, we cut it out then.
No, we're including
And then we cut it out to get the exact measure.
So just think of it as a rectangle and ignore that it's not.
So then we have to cut that out.
Don't cut them, just leave it in like a rectangle. Make it a little easier.
So then, how much of that room would go out? So somebody does the length, somebody does the width.
So is your group lacking rulers? No, you have each other.
You're not very good.
Go into a classroom.
Yeah.
Or maybe we could do ourselves at high time. I think I'm one.
And we also have to count out like, so like, we're not counting the front.
Square with all the way?
Yes. Yeah.
Everybody else would do that. Some of these are.
Yeah, we have to also measure.
Please, I don't know.
We're at 25 and a half.
I don't know exactly what color I am. I don't know exactly what color I am.
Other tiles for you? Are they square feet? Other tiles square feet? I love those tiles.
Oh, That's not, well, how much is it? How much is it?
Sometimes I give them
Oh, do
money.
it in feet. Do it in feet. Yeah, do it in feet. That's what most of them do then. Then you'll be able to compare with others.
Whatever we get.
Are you like a third grader?
I looked in my math education.
Oh, okay. So you're like, you're not used to like
No. The imperial system?
We're just.
No, you're just sorry.
Everybody else feels like yeah. The problem is when they make the child or they kind of cut off some parts of it.
But this one's
Just an approximation.
So what do you need to make square foot?
And then these are the 104 inches. We have to,
So a foot is 12 inches. 30,
when you multiply it into 12, you get
like, how do you have it?
we're doing 104
We're estimating
tiles.
So do you want just round it up to 1 foot?
And do you need it?
Sure. However you
That's
prefer.
probably the best count. How many tiles?
Maybe we should measure in dog tails or something more useful. Okay. No, different kinds.
Yeah, just more of the 104. We just would have to multiply it 12 and add the 25 on the 42.
43, we have the weird big ones.
Okay, so two of these squares, one,
No, it's actually in inches. Well,
You got 3 different numbers here.
Alright, now,
That's triangles.
1 3 inch.
maybe we could share the meters.
Well, what if you measured up to like for this part?
We could use the meters.
Do you want me? Because if this is actually
Excuse me.
I thought it 24 times.
Alright.
Okay, let's work together on this, okay?
Multiply the 104 by 60.
Let's work together and present the measurements and we'll compare and we'll try to get confirming amounts.
How many balls got thrown and how many chicken categories?
Okay, how wide was this room? 40, what did you say? 42. Anybody else get 42?
42 tiles.
42? Are they square feet? Okay. And how about this way? 24? 25?
Yeah.
Anybody else get
Yeah, 25.
25? Okay. Okay, and how tall was the room? How tall was the room?
104 inches.
104 inches? Anybody else get 104 inches? What did you get?
About that.
About that? Okay, you got about that? Okay. Okay, so when we're measuring, we want to have all the same units. So let's switch all of our feet into inches. Okay. So 25 feet times 12, how many inches would that be? Where's my calculator? You got that one? What is it?
300.
300.
Thank you. How many inches was 42 feet?
504.
Anybody else get 504? Okay, good. I always look to confirm these things. Otherwise, I'll get an email later saying I was wrong. All right, so I was gonna. Okay, so we'll find the volume. Now, when you're doing volumes, you do the length times the width times the height, which I think you knew that, didn't you? A lot of you did. Okay, so length times width times height. So your inches multiply too. So you have inches times inches times inches. We get cubic inches that way. Did anybody get a number?
15,724,800.
Anybody else get that? Nobody else get that? Let me try once. You got that?
Yeah.
Okay. So cubic inches, when we say a cubic inch, we mean a cube that's an inch in all three directions. So that's how many cubes we could fit in here. But we didn't have cubes, we had ping pong balls. So how big were the ping pong balls? Did anybody measure their ping pong ball? Oh, look at this one has a face. Okay, 1.5 inches. And that's the diameter, right? Now, when you stack the ping pong balls, though, you can see in this box that they stack next to each other. They'll jiggle around a little bit, but we can think of them as cubes themselves, just to get a good approximation. So we can think of them as cubes. Did anybody multiply that out? I feel like I did that earlier. Is it 3.725?
Yes.
Thank
No,
you.
3.375.
What is it?
3.375.
Oh, thanks. Okay, so now we know how much volume we have to fill. We know how much the balls will take up if they all lined up exactly perfect. They'll shuffle around a little bit, but again, that's going to be a good estimate because we're taking away some space, adding a little space, shuffling the balls a little bit. So we'll get a good ballpark estimate. So let's go ahead and divide the volume by the size and see what we get. So we have 4,659,200. Look at your guess. Did anybody guess 4 or 5 million? No. I would have just looking at this and looking at ping pong ball, I would have thought like 20 million or something like that, right? So if you guess, nobody guessed in that range?
Well, we got 5 million.
Oh, that was a good guess. That was a very good. Was that with your work or was that your guess at the beginning?
Our work plus our guess.
Very good. Okay. Anybody else get that when they were guessing? So what we see here is that your guess doesn't necessarily get as close as if you add information in and do a little work to get some more details and finesse your guess. So now our estimate is way closer than like what I would have guessed at 20 million. Our estimate is much closer than what my guess was. Well, we're going to use this idea of not knowing exactly but getting a good approximation in order to answer a question. So let's look at the next question the author proposes. Are there two non-bald people in the world? Are there two non-bald people in the world who have exactly the same number of hairs on their bodies? Are there two non-bald people in the world who have exactly the same number of hairs on their bodies? So again, a guessing game for you. I'd like you to write down yes, no, or cannot be determined. Okay, so write down what you think that is. Yes, no, or cannot be determined. No fair reading the answer. No, good work printing it out and being prepared for class, really. Okay. Well, here's how we're going to work this out. What we're going to do is we're going to find the most, what are the most Okay, so we're going to figure out what are the most hairs possible on a human. And the way we're going to do this in your groups, we're going to pick somebody who doesn't mind having their hairs counted. And you're going to take your ruler. So where's your ruler? You take your ruler, and on their scalp next to their hairline right here, okay, where you can peel your hair back and you can see the edge of your hair, okay, measure out 1/4 inch by 1/4 inch. So we'll need to measure out 1/4 inch by 1/4 inch and then count the number of hairs in there. So we need someone in your group who's okay with having their hairs counted, and we need someone in your group who doesn't mind doing the counting, and we need somebody with a ruler to help measure. Okay? So same groups. Figure this out. We're gonna walk around and see how you're doing.
I can touch my hair, so you don't have to. I prefer you not.
So what was it again?
I'll do it.
It's a plus.
Yeah.
How many? Also just counting all the hair. But then how would you decide?
Okay.
I got about 6 in my
Okay, so I'm not. Okay, your group is
Well, let's just like install.
You already have your food back.
You take off your jewelry.
Okay, that's all right. So in your group, nobody wants to.
Well, I mean, we can go on here, we'll be here.
We're just doing a little piece, little piece.
Yeah, I was about to say that.
Just take a little piece.
What is 1/4?
Well, that would be a way to do it, maybe. Blow up a picture, like, get more. That might work.
They're only like halfway there.
But then nobody shall keep me out. I don't know.
I'm trying to draw that logo and I can't find
Yeah, just take it.
Trust me, it's not. It's about that. Yeah.
All right, well.
And there's some baby hairs.
Make like a border of it, divide it.
I don't understand how you're supposed to like figure out like.
Okay, is there anyone who's willing to do the measuring and counting here?
Cut it off.
So we measure 1/4 up here and then count.
No, I need to set the border. Like, pull the hair out. Hold on.
Well, that's good.
Grab big chunks.
Like 35. Like each individual straight.
You guys are to do a 1, 2, 3, 4.
Well, I like took a whole, like I took like a little piece, and then I was like counted how many of those pieces would be in that like.
I mean, because if you can see it, it's like, more sitting on here like red, and they're not going to be palms ball.
Don't touch me.
Like one row, you want to instead of doing that.
No, my hair is short.
If you feel too weak, if you don't mind, I'll come to breathe.
Yeah.
Oh, 57.
57.
57, you're done?
Yep.
Coming way out.
57? I got it.
Okay.
You're still counting? No, I can't. Okay, do the bathroom count?
I counted whatever I could find.
Do you remember what you got?
17, or no, 27.
27, 57.
That's a great.
Okay, that looks like That's okay.
You go the whole person, like all the fours.
In my group.
What's your major?
Yeah, I got a lot of big hair. That's like big head. Big head.
There's all the segments of that do I have on my head?
I don't know, my brain is.
Okay, so you counting the 107 little segments. How would you figure out like segments that I have on my head?
Not going to
I haven't been here, but like a lot of cities.
I think 102. Did anybody find more than 102 in their groups?
No.
And thank you for being countable. Okay. All right. So 102 was the most we found in this class. Okay, so the most we found in our class was 102. And what we're trying to do as our first step is to find the most hair a human could have. Okay. So if the most we had in our class was 102, can we all agree that nobody would have more than 10 times that? Nobody would have more than 1,020, right, in their little quarter inch? Does that seem reasonable? Okay, so the most possible hair would be something less than 1,020 in the 1/4 inch by 1/4 inch. Well, let's see what that gives us then for a square inch. So let's go ahead and draw a square inch. So a square inch is like on your tile floors. You have square feet, tiles. They're 1 foot by 1 foot. So a square inch tile is 1 inch by 1 inch. So how many 1/4 by 1/4 sections are there in the square inch? Let's just draw it out and see. So I'll divide the square inch up into 4 1/4. So how many does that make?
So 16.
Yeah, 16. And you already did the multiplying? Good. Okay. So 16 1/4 by 1/4. So the most anybody could have on a square inch of their body would be 16 times the 1,020, which you said was 16,000 what?
320.
16,320. So that's the most hairs on any square inch. Okay, now we have to figure out how many square inches of skin you have. Okay, who wants to get measured? No, I'm just kidding. Okay, we're going to draw Bob. Bob is in your textbook here. Bob, yes, Bob is a cylinder. So he's easy to measure. So Bob is 6 feet tall and 42 inches around. Okay, so we're looking for square inches of skin here. So if we unrolled Bob's skin from around his body, it would make a rectangle, because Bob's a cylinder. So let's see, 6 inches, 6 feet tall is 72 inches. 6 times 12 is 72. 42 inches around. I just took 42 inches because that's the size coveralls my husband wears. So I think I think that's his measurement around. Alrighty. So 42 inches around and 72 inches tall for that rectangle of skin that's around Bob the cylinder. What does that give us? 42 times 72. So 3,024 square inches around, and then there's the top of the head and the bottom of the feet. So from here to here is about 7 inches, the radius. Does anyone remember the area of a circle formula? Yeah, something like that. That's a circumference. Yeah, pi r squared. Did someone have it? Good. So that's 154 square inches. So that'd be the top of Bob's head and then the bottom of his feet. So we have Bob the Cylinder's skin would be 3,024 plus 154 plus 154, or 3,332 square inches of skin. Now, Bob is a cylinder, and we're not cylinders. We have, for example, necks, right? So we have more skin than Bob, or less skin. Maybe we're smaller people than Bob. But nobody would have 10 times as much skin. Because, I mean, even if you had 10 times as much skin, so you had all that skin, you're likely putting all that energy of your body into growing skin and not hair. Okay, so so we'll say that nobody has more skin than 33,320 square inches. Okay, so that's a pretty rough estimate, but we can feel confident that nobody has more square inches of skin than that. If you want to double check that, you can go home and do more careful measurements and report back. And nobody has more hairs per square inch than 16,320. So the most possible hair a person could have would be to have these 16,320 hairs on every square inch. So that's 543,782,400 hairs. The most possible hairs a person could have, and possibly more than a gorilla even. Now, go back to our original question. Where was that? The question we're trying to answer: are there two non-bald people in the world who have exactly the same number of hairs on their bodies? We have the most possible number of hairs, and there are 7.6 billion people. So now that we have more information, can you answer that question yes, no, or impossible to determine? Anybody have any ideas? Yes.
I say it's pretty unlikely that we'd be able to determine that. It just does. It seems like there's too many people, and I don't know. It doesn't. It kind of seems like a snowflake effect. Like there's not one person who has the same amount of hairs as another person. That's just a guess.
So you think it's unlikely, and then it's even more unlikely that you could tell whether it is or not. Like there's not enough information.
Yeah.
What do you think?
I'm saying for someone to not be able to, like, if it's not possible to exceed that amount of hairs, there's likely a possibility that somewhere in the world, because there's such a large population, that you will find perhaps a case where there isn't. Because if they're not going to go over the limit, then they're likely going to stay in that range. And as long as they stay in that range, with so many, 7 million people, there probably is a possibility to find someone. But I find it so weird just because they're also talking about body hair too.
Yep,
And
all your hair.
there's all kinds of factors, like people grow different kinds of body hair, different areas. So if you're basing each unit, each person in the world, 7 billion people, on being the same kind of person, how they grow their hair, then it probably would be possible. But there's just so many other factors.
So there's a lot of factors.
Theoretically, yes, but in real life, I don't know.
Okay, so you're still a little iffy there.
I'm saying yes. 'Cause
You're saying yes.
In theory.
Okay, yes in theory. Anybody else have any? Yes.
I'm going to say no, because if you're looking at the religious view of it, God makes everybody different, and there's not one person who's the same.
So everybody's different.
There's not one person who would have the same amount of hairs.
I agree that everyone's different, but let's see what the pigeonhole principle tells us. So how about we do this? How about we take everybody on the earth and assign them a room, and they're assigned their room based on how many hairs are on the body. So these are all the non-bald people. So the people with 1 hair go in here, the people with 2 hairs go in this room, the people with 3 hairs go in here, 4 hairs in here, 5 hairs in here. In fact, we have a lot of rooms. We have a room for the most number of hairs possible. 543,782,400 hairs go in there. And the people with 1 hair less go in here. And so on. So we have everybody assigned to a room based on their follicle count. We all fit in there somewhere because we figured out nobody has more than this many hairs on their body. So these 706 billion people all get put in a room. There's 543,782,400 rooms. Anybody want to think about what that means?
Multiple people will be in the same room.
Yeah, there has to be at least one room with multiple people, because there's not enough rooms for everybody to have their own room. So in the room where there's multiple people, those people have the same number of hairs on their body, because that's how we sorted people. We sorted them by their hair count. So the answer is yes. And we don't, there's a lot we don't know. We don't know who the people are. We don't know how many hairs they have. But we do know definitively that there are 2 people on the planet that have the same number of hairs who are not bald. This is an application of the pigeonhole principle. Admittedly, a weird application. But the pigeonhole principle is used in making definitive answers like this. Even when we don't know the specifics, we can still say things definitively that are useful to us. Let me write out the pigeonhole principle so you have it in your notes. If we have more objects, than we have boxes.
It went away now.
Thank you. If we have more objects than we have boxes, at least one box must contain at least 2 objects. At least one box must contain at least 2 objects. So we'll see different applications of the pigeonhole principle. Let's start with one about birthdays. How many people are needed here to ensure a shared birthday. How many people do we need to have in this room to ensure a shared birthday? And I don't mean the year, I mean the day and the month. 366, or if we count leap year 2, then it'd be 367, right? Because if you put a box for every day of the year, January 1, January 2, January 3, till you get down to December 31st, and you have everybody go in that box with their birth date, well, there's only 366 boxes if you count leap year. So one of the boxes at least has to have 2 people. Now we don't know what box, we don't know how many people are in that box, but we know at least 2 people would be in one box. How about if we do just this classroom? Let's look around in this classroom. Must 2 people in this room have the same day of the month for their birthday? Like my birthday's on the 27th. Does that mean there has to be someone else in here with the 27th? Now there could be, but does there have to be? Well, it depends how many people are in here. It looks like we have a full classroom. Let me count. It's going to be close. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 31 people here. So must 2 people in this room have the same day of the month for their birthday? There probably are, but not. They don't have to be, right? I could be the 27th, and everybody else could be a different day because there's 31 days. How about if I change this to week? Day of the week. So then there's only 7. If you knew what day you were born on, would there have to be other people here born on the same day? Yeah, then there would, right? Because then there's only 7 days, 31 people. Okay, so we'll look at a few more questions on the Pigeonhole Principle on Wednesday. I'll see you then.